Hi everyone, and welcome again to Nettle, the go-to place to learn about business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters and YouTube members for making this video possible, and we'd also greatly appreciate if you consider supporting us as well. So please click the link in the description or click the join button below for more details. My name is Sava, and today we're investigating a fundamental extension of the heterogeneous autoregressive volatility model, which is the HAR model we have got a tutorial on the simple implementation for. However, today we're discussing the HAR-RQ model, or HARQ for short, which has been proposed quite recently in 2016 by Bollerslev et al. In their famous Journal of Econometrics paper. The idea behind the HAR-RQ model is to account for the measurement error that is present in modeling of realized variance. Again, one of the strengths of the HAR model is that it uses realized variances instead of conditional variances that something like Gauss models are famous for. This makes the implementation of the model very simple and intuitive. You could just use simple OLS without having to resort to maximum likelihood estimations that are harder to interpret and estimate. However, there is the problem of measurement error, as the independent variables which are lagged realized variances in the HAR model, we have got them here in the equation. These realized variances are estimated with an error, and this leads to biased estimations of the model coefficients. That can be problematic for forecasting, and therefore Bollerslev et al. Suggested a simple adjustment that deals with realized quarticity, which is the fourth moment of our return distribution. Estimating realized quarticity is very simple. It's analogous to realized variance estimation. However, you are concerned with the fourth moment and not the second moment, so you quite naturally just square your returns. And for the HARQ model, there is no way around using high-frequency data to estimate realized variances and realized quarticities across trading days based on more high-frequency input. And for today, we'll use hourly data, as this is the most simple high-frequency data input that we can still use to provide quite an interesting and practically relevant implementation of the HARQ model. So without further ado, we have got a bunch of hourly data. So we've got hourly Bitcoin prices from year-end 2018 until year-end 2022, totaling more than 35,000 rows. And we've got hourly prices. So we'll need to convert those into, respective daily realized variances and realized quarticities. And for that, we'll work on two separate sheets. So on the hourly data sheet, we'll first map those hourly candles to relevant trading days. And for that, we can simply use the quotient function, simply discarding the time part of the date time variable and leaving ourselves with simply the date variable. That will make it easier to calculate realized variances and realized quarticities using some if functions. So here we can see that we have avoided recording the time and we're just stuck with the date itself. So for example, if we estimate in realized variance or realized quarticity for the 1st of January 2019, we'll quite naturally just look at those 24 candles that are hourly candles for the 1st of January. Again, if you're dealing with a conventional financial time series that has got weekends or that closes for the night, you'll have a smaller number of hourly candles, and this approach would also allow you to construct them quite seamlessly. Now for hourly return, we just divide the price at the end of this hour by the price at the end of the previous hour and subtracting 1. Then we might want to convert it into percentages so that our numbers are not very small and are easier to interpret. So here I'll just multiply both by 100. So this means that the return in the first candle we have got is 12 basis points, or 0.12%. Now we square those returns and also raise them to the fourth power for the calculations of realized variances and realized quarticities respectively. This completes our task for the hourly data sheet, and now we can use our calculations to calculate realized variances and realized quarticities for every single sample day. So for the realized variance, we simply apply the SUMIF function. We refer to the range of dates or days in column B here. We want that to be equal to the day we are currently at, so that's the A2 cell, and then we refer to the squared returns that we've got in column E in our hourly data sheet, and we lock them both rows and column-wise. And that allows us to calculate realized variances for the entirety of our sample period. For the forecast cell, we'll delete it for now, as we'll calculate it based on our HARQ model output. In this sample, we do not know what the variance is on the 1st of January 2023. The goal would be to forecast it using the HARQ model. For the realized quarticity, we use a very similar approach. Here, we need to take into account how many periods are there in our high-frequency data. So as we are using hourly data and mapping it to daily periods, we'll need to use 24, as again, Bitcoin markets are open 24/7. If you were using something like an S&P 500 data, you'll do 7 or 8 hours, depending on for how long the markets are open at a particular trading day. Again, you need to keep that in mind when calculating quarticity. So for the realized quarticity, again, we calculate, first of all, the adjustment factor, which is 24 divided by 3. Again, M equals 24, as the Bitcoin market is open for 24 hours every single day. And we times it by the SUMIF function. We apply it again to our day column from the hourly data sheet, locking it both ways. We refer to the day we actually care about, locking the column. Then we refer to the returns to the fourth power in the column F from the hourly data sheet, and that completes the calculation. We can calculate realized quarticity throughout our sample period. And now we can lag those values appropriately to estimate our HARQ model. What we need, just as in the conventional HAR application, are the lagged daily, weekly, and monthly realized variances, as well as interactions of those with appropriately calculated realized quarticities. And we need to calculate the square root of those. As again, realized quarticity can be conceptualized as variance of variance, and therefore if we are interested in volatility of variance, we quite naturally take the square root of the realized quarticity term. So for daily realized variance, we just refer to lagged realized variance in the previous trading day. That's quite simple. We can enforce it throughout immediately. For the weekly realized variance, we need to keep in mind how many trading days there are in a trading week for our instrument. Again, if you were doing it for stock indices, bond indices, markets that close for weekends, you'd take the average of the past 5 trading days worth of realized variance. As we're dealing with Bitcoin, again 24/7 trading, we'll go for 7 lagged realized variances and average them out. So here we can see that we can have 7 lagged realized variances for the first time in row 9. So we just calculate the average of the respective cells. So the average of lagged 7 days worth of realized variance. And finally, for the realized monthly variance, we'll need to again estimate how many trading days there are in a month. For Bitcoin markets, that would be around 30, as a calendar month is a trading month. For US stocks, you would go for something like 21. For European markets, you would go for something like 22. Again, reflecting the initial specification of Corsi in 2009, who proposed it for European markets, most notably Swiss foreign exchange and bond markets. So we need to take into account when do we first have 30 days worth of data. Here we see that 31st of January is where we can refer to 30 lagged realized variances. So that's the first time we calculate the average of the past 30 realized variance terms. And now we can implement our interaction terms. So first, we refer to the square root of lagged daily realized quarticity times our lagged daily realized variance. Again, we can just refer to the cell itself, or we can refer to the lag term that we have already calculated. That would save us some time and effort. This we can first drag so that Excel recognizes we can bottom right click it, and that's what we do. For the weekly realized quarticity, we need to start exactly at the same row where we have got the first weekly realized variance term. We implement the square root of the sum of lagged weekly realized quarticities, so the sum of the 7 lagged cells, and times it by our realized variance on the weekly frequency. That allows us to immediately enforce it throughout the sample. And finally, for the monthly term, we can calculate the square root of the sum of 1 month worth of realized quarticities. Here we've got them, 30 terms indeed. And then we times it by our monthly realized variance. And that's pre-processing done for our model estimations. And now we can proceed with the model itself. Again, just keeping in mind to delete the final row that we will use for our forecasting. First, to compare our HARQ model with a reasonable baseline, let's estimate the conventional HAR model as in QuartC 2009. Here we do not take into account any of the realized quarticity terms, and we just deal with daily, weekly, and monthly realized variances. That would mean we have to select a 5x4 template for our linist to work properly. Again, 5 rows, it's always the case for linist, 4 columns because we've got a constant, which is unconditional realized variance, and 3 explanatory variables, daily, weekly, and monthly lagged realized variance. We use the linist function. We'd select the first day with realized variance available and all 3 lagged terms defined. So we refer to this array of dependent variables, and we refer to the 3 independent variables, which are daily, weekly, and monthly realized variances that are lagged. Then we input 1 because we want the constant, that's our unconditional variance estimator, and another 1 so that we get the additional statistics such as standard errors and the R-squared. We enforce this function and try to interpret the results. First of all, we can calculate the t-stats for individual coefficients, dividing the coefficient values by the respective standard errors. And we can test for their significance using a two-tailed t-distribution, inputting the absolute value of the t-stat, as well as the degrees of freedom that is reported as the rightmost element in the 4th row of your linist template. And we need to log the column here as the residual degrees of freedom is the same for every single coefficient t-test. Having applied those, we can see that there are very significant positive effects of lagged daily and lagged weekly realized variances, which means that there are notable persistence effects there. Again, these are significant 1%. The effect of realized monthly variance is positive yet insignificant, meaning that for Bitcoin markets, the variance persistence, or at least the realized variance persistence, is a little bit more short-term than what has been calibrated by QuartC on conventional financial markets, most notably in Europe. However, this particular estimation is vulnerable to biases associated with measurement errors in our lagged realized variances. Again, whenever there is a measurement error in your independent variables, in your X variables, this means that the estimators are biased. And that can be addressed by introducing the squared realized quarticity terms that proxy the estimation error of realized variance. Again, because realized quarticities are variances of variance. Again, they can be conceptualized as such using the logic of higher moments. So that's the extended Bollerslev HARQ estimation, where you introduce 3 interaction terms based on daily realized quarticity interacted with daily realized variance, weekly realized quarticity interacted with weekly realized variance, and monthly realized quarticity interacted with monthly realized variance. We can select a 5x7 template now, as we have got 7 coefficients to estimate, 3 additional explanatory variables, and we input our linist function. Again, the dependent variable is the same, just the realized variances. And our independent variables now include 3 additional columns where we have got our square root of realized quarticity interacted with realized variance. Inputting those 6 allows us to then specify that we need the constant, unconditional variance, this concept stayed the same, and 1 for additional statistics. Now we enforce this function, and can interpret the new model output. Quite similarly, we can calculate individual t-statistics and plug them into a two-tailed t-distribution, and we can see that the realized quarticity effects are significant for weekly and daily terms. The significance of our daily and weekly realized variance does not change much in terms of the statistical significance. Both are significant at 1% still. However, we can see that for this particular estimation, the coefficient for weekly persistence and daily persistence are changing in terms of their magnitude. So the daily persistent coefficient is quite a bit lower, weekly persistent coefficient is quite a bit higher. But again, this is further mitigated by the effects of realized quarticities that these coefficients demonstrate. These both are significant, whereas the term for the interaction effect for monthly realized variance is insignificant, just like the original coefficient beta m, that again used to be insignificant in the conventional HAR application and is still insignificant in the refined, extended application of the HAR-RQ. What Bollerslev et al. Also found is that most of the time it's not necessary to include all three interaction terms. You can do just fine by including the daily interaction term, and that attenuates most of the measurement error effects and leads to a reasonable model that can be used in forecasting. So let's try that. Let's estimate a reduced version of a HAR-RQ model where only the daily realized quarticity interaction is included. That allows us to select a 5x5 range of cells, and again, linest function it is. And we can refer to our three original explanatory variables plus the daily interaction with quarticity. 1, 1, enforcing the function and interpreting the t-stats. Here, everything apart from the monthly persistence is significant quite nicely, and we can also compare the R² terms of the three specifications. We can see that all three models explain around 25% of the variability in realized variance. For Bitcoin markets, that's quite impressive. We can see that the extended model has the highest R², and it does have an additional significant term, so perhaps for Bitcoin it is wise to go for a more extended version with weekly quarticity interaction included as well. However, the reduced version is also a good extension over the baseline HAR, as in Corsi 2009, as it has got a significant interaction term with the daily realized variance. So finally, for the forecasting implementation, let's use the extended version just for the sake of the concept. Here, what we can do is drag the explanatory variables down by 1, and we can see that they would still use real-world data. They would not feed in any prior forecasts into it, which is quite nice for forecasting accuracy and the interpretability of the model results. And now we can simply calculate our forecast. First, we need to input our unconditional variance term, which is the constant. Then we can multiply our coefficient times the explanatory variable and continue as is. So we can select the second coefficient in our extended HARQ model. That would be the weekly persistence, times it by the weekly lagged realized variance. Then we can refer to the monthly persistence, times it by the monthly lagged realized variance, and then account for interaction effects. So our daily interaction term times the daily interaction variable with realized quarticity, our weekly interaction term times the weekly interaction value with realized quarticity, and finally our monthly interaction term times the monthly interaction with realized quarticity. That generates a forecast of 4.09. So realized variance is 4.09, meaning that our volatility would likely be around 2%, so square root of the realized variance. And this is how simple the application of forecasting for HARQ models is. ultimately it's a little bit more challenging for HARQ models instead of conventional HAR models, as you cannot really forecast your realized quarticity this way. However, one step ahead forecasts are also quite straightforward and intuitive. And this is all there is for the application of the extended HARQ model based on high frequency data, its comparison with the baseline HAR model as in Corsi et al., and the power of realized quarticity to address the measurement error effects associated with realized variance estimation. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions for videos in business, finance, or economics you'd like me to record. And please don't forget to subscribe to our channel and consider supporting us on Patreon. Thank you very much, and stay tuned.